Hello there, math fans. As I was going through some old materials today, I found this little project I made for a course in proofs. This was a course where we introduced all types of proofs and logic to get students ready for upper level courses. And I always found in that course it was challenging as an instructor to find questions that were interesting and didn't require too many skills, too many tools, and allowed students to think about proofs. And I was pleased that I was just happened to be thinking about, I don't know why, at some point was thinking about this idea that there aren't very many whole numbers where when you add them together and multiply them together, you get the same thing. And you might think about such a thing. And I had just been toying around with this idea of, well, what if you kept going? And I can't remember if I'd ever seen that before. So then I played around and found a solution. And then I tried to think about, well, what if you keep going? And I played around with it, found some solutions. At some point I figured out, I searched and I found that this was a known problem and that there's actually some unsolved problems relating to it. That must have been like 14 years ago when I was doing that. So maybe some people have solved some of those unsolved problems, but I can't remember how I searched and found this. I could have spent some more time, but I just wanted to put this project up because I think it's kind of interesting and it's something maybe my calculus students would appreciate that gives a peek into this idea of generalizing and doesn't require any calculus or anything, and it's sort of interesting. So I will solve those three situations provided I can remember how to do it. I will use my little worksheet as a guide. I think my handwritten solutions are somewhere on paper. This is before we scan things. So anyways, and this doesn't require too many skills, and it might be kind of interesting. So you can try on your own to find positive whole numbers, is what I'm talking about, that solve these. And then when I made this project, I always like to come up with goofy names. I called it Where Sums and Products Meet. Okay, so this one you've probably seen. Maybe you've never thought about this, but the fact that 2 plus 2 is equal to 2 times 2. Now in math, I'm claiming this is the only solution, but that's a big challenge of how can we prove that that's the only solution? And what I liked about this proof, it was fairly constructive. Like it'll show you through a matter of just a few bits of logic that those can be the only ones. You might wait, I'm not going to give away the answer here, and think about what those solutions are, and then think about would there be solutions for higher variables, and it turns out there's some unsolved problems. Not so much unsolved problems in that people haven't found solutions, but unsolved problems that sometimes there's more than one, sometimes there's kind of some interesting things there. Okay, this was a journey through trying to generalize this idea. Okay, so the project started with me saying, we're going to explore this. Can you come up with numbers that do it? And I'm going to talk through this proof and try to make it more clear. And this is kind of an introduction to proofs. This is not really for a Calculus 2 student. I have a little box there to say I'm done. And it's written in a way that a math book might write it, a higher level math book for space. But that's hard to read. So it says, you assume you are trying to find solutions to this. One of the numbers has to be less than or equal to the other number. So we use this funny phrase, without loss of generality. We mean whichever one is the smallest, let's call it x. Whichever one is greater than or equal, let's call it y. And we say we're allowed to do that because we're just naming them. Okay, so without loss of generality, we say this. And then we're going to make a little argument about the sizes of the numbers. You should sort of have the idea of a proof sometimes is hard because you can play around with different numbers. Like, why doesn't it work for 3 plus 2? Well, because the product is too big. And for most numbers, the product is big. So we kind of would like to make an argument about size, but it's unclear how we would do that. So we say, if you have this, and now we're going to do a bit of logic to try to reduce what we have to search for. And I'd say this is a pretty unusual proof, but there are some things that are like this. So here's what we're going to say. If you add the same thing to both sides of an equation, a positive number, that doesn't even matter, it's still less than or equal to. So we're adding something to both sides. I think I probably can convince everybody of that, but if you added 2 to both sides, the thing on the left is still smaller. Okay, so there's 1. And this is 2y. So we can conclude that x plus y is less than or equal to 2y. Okay, that's fine. Now we're going to look at it another way. So we'll call that fact 1. So that's what we can say about the sum. Can we say anything about the product side? So we're going to kind of look at that and see what we can say. Well, so this is the part I think that's kind of tough, but we say, well, we know that it works for 2 and 2. What if you went bigger than 2? Let's see if we can reduce what we have to check. So are there any solutions where x is bigger than 2? Well, if that were true, then you would have 2y is less than xy. That's because we're multiplying both sides of an inequality by a positive number. We're trying to solve this for positive numbers, x and y. If it's a negative number, it would switch. So this is, again, part of that course. We'd already talked about some of the axioms of inequalities. And so that's really all this proof requires. And then we got to use the so-called transitive property, which is if this is less than or equal to 2y, and 2y is strictly less than xy, then what can we say? Well, we can say x plus y is strictly less than xy. And so what do we conclude from that? We conclude that this is not possible. It's not possible for x to be greater than 2. But that really restricts things. So the only way it's possible is if x... So what we just proved is that x has to be less than or equal to 2. But that dramatically reduces things. So first we try what if x is 1. So this is kind of an unusual proof that we reduce things so much. Okay, so if x is equal to 1, then you would have 1 plus y is equal to y, and you'd have 1 equals 0, and math is wrong, and we can all go home. No, the conclusion is x can't be 1. And if x is 2, and you solve, you get y is 2. So that's the only solution. It's a nice little bit of logic. So x has to be less than or equal to 2, and 1 doesn't work. And 2 works, and it gives 2. So the only solution to the 2D, 2 variable, when sums and products meets, is when they're both 2. Okay, so what interested me in this was I never really thought beyond that. And just one day I had the thought of what if we go further? So now let's try the same thing for 3. And I would encourage you to experiment if you haven't yet. And I remember thinking, oh, it's probably the same sort of pattern. It's probably just something to do with 2 or it doesn't work. I remember that. I vaguely remember those first thoughts. But I was just sitting there, having lunch. I can't remember what I was doing. And I happened upon one solution. I think this was one. Let's see if I can remember it. This one. Nope, that doesn't work. 1 times 1 times 2 doesn't work because this one would be 4 and that would be 2. So can we do any better? Well, if you do, how about... I didn't intentionally give the wrong one. How about 1, 2, and 3? And that's actually a really important number. That number 6 is a perfect number. It's the sum of its divisors, proper divisors. So that is a nice solution. Is that the only one? I don't know. So you start to think, well, maybe it's always just numbers in order. But before we start to generalize, let's see if there's any other solutions here. So we play the same game. Without loss of generality, let's assume we label the 3 numbers, the solution, in this order. And by a similar argument, we can say that x, so now we're going to kind of attack the left-hand side. And it's not the most clear argument. I had to think about this a little bit, is less than z plus z plus z, which is 3z. So x plus y plus z is less than or equal to 3z. And there might be improvements on this type of proof to reduce things even more, but let's just go with what we did last time. Now let's think about what we can say. So we have a solution with 3, and we'd like to say we'd like to not have to search beyond that. So if we have a solution, and this is the part that's tough, we're trying to somehow relate it to this side. So we say, well, what if this stuff together, and like I said, this is not an obvious proof to me. I had to experiment around to make the inequalities work. Then what can we say? Well, we can say 3 times z is strictly less than x, y, z. And that, if that's the case, and this is less than that, and that is less than this, then x plus y. So it's a really interesting proof of just saying, if the numbers get too big, it's not possible, but this gave us a precise way to say it. So what is the conclusion? The conclusion is that xy has to be less than or equal to 3. And they're whole numbers. So there aren't very many ways you can have two whole numbers where their product is less than or equal to 3. In fact, now that I look at this proof, I think I did a bad job here. Because some of these solutions don't make sense. 3 and 3 doesn't make sense because the product is 9. This doesn't make sense. This doesn't make sense. I don't know why I included extra ones. I guess in some ways my proof isn't wrong. It's just dumb. And we also know that x is less than or equal to y. So the only things I really need to try are, what if x is 1? And y is 1. Does that work? We just tried that, and 1, 1 didn't work. Because if this was 1 and this was 1, we would have, so let's write it, 1 plus z is equal to z. Okay, that's not possible if you plug in a 1 in all the places. Okay, 1 plus 2 plus z is equal to 2z. That is possible. That's this 3 plus z equals 2z. So z is 3. And that's the solution we found. So that implies that z is 3. And that gives us one solution. 1, 2, 3. Let's write it that way. So the only other thing to try is 1 and 3. So what about 1 and 3 plus z equals 3z? And you solve, and you get 4 plus z is 3z. And you get z has to be 2, but that's the solution we already got. So this is the only solution. So far we've learned that 2 plus 2 is 2 times 2. And 1 plus 2 plus 3 is 1 times 2 times 3. And those are the only solutions where sums and product meet for 2 and 3. So let's keep generalizing. Again, you might say, who cares about this? This is more of a journey in generalization. These are examples of what are called Diophantine equations. Equations where you're only allowed to have integers. In fact, we're being more restrictive here. We're only allowing positive integers. And in general, it's very hard to prove things about these. But they are important. There's a lot of situations where whole numbers are the only numbers that make sense. So let's see what happens when you go to 4. And this is when things get kind of interesting. So I guide students here and I say, okay, now that you've seen a couple examples, and it might be harder to find solutions, you're encouraged to try, maybe you can just go straight to the proof. Meaning, can we do the same sort of thinking we did before? So what was that thinking we did before? First we said, well, without loss of generality, let's label them in increasing order. And then let's see if we can reduce it down to something about one of the variables. So let's say, let's assume that x is less than or equal to y, is less than or equal to z, is less than or equal to w. Now we're trying to generalize. And this would be less than or equal to 4w, because each one of those is less than w. And now let's attack the other side of the inequality, because we'd really like to say this is less than x, y, z, w. And maybe we can play the same game. So if x, yz is greater than 4, then you would have, multiplying by w, 4w is less than xyzw, and that would mean these two things can't be equal. And from that, we conclude this isn't possible. So that means that xyz has to be less than or equal to 4. And now we've reduced what we have to search by quite a bit. From an infinite number to a few. So now let's think about the numbers that work there. So you could have, and maybe we'll list out the equation, y plus z plus w, and we're trying to find numbers where these two things are equal. So if this is 1, and this is 1, and this is 1, so that's the smallest numbers, and the product is less than 4, then you'd have 1 times 1 times 1 equals w, and that's not possible, because you'd have 3 equals 0. So 1, 1, 1 doesn't work. What about 1, 1, 2? The product of those three things is still less than 4, and then you'd have a 2 over here, because this would be 2. Is that possible? So you'd have 4 plus w is 2w, and you'd subtract and you would get w equals 4. So that works. So we have a solution. 1, 1, 2, 4. And that's when things kind of become interesting, because if you think about our first solutions for 2, they were this and this. And this one is kind of weird because you have this repeat 1. 1 times 1 times 2 times 4. And they both give you 8. So it's not a perfect number. It's not this weird thing with 4s. It's something different. Are there others? Okay, so we tried 1, 1, 2. If you try 1, 1, 3... Oh no, we haven't tried 1, 1, 3. Let's do that. So let's try 1, 1, 3 plus w is 3w. That gives me 5 plus w is 3w. So that gives me 5 is 2w. And w is 2.5. So it's a solution, but it's not a whole number solution. So you get this 1, 1, 3, 2.5. So we're not counting that. We're just looking for whole number solutions. So that's no good. So we've ruled that out. What about 114? If you do 114, you're going to get 2 because we already saw that. So we're done with that one. So let's see where we're at. We've done all the 1-1s. 1, 1, 2, 1, 1, 3. So now we should do the 1-2s. And it feels like this is going to take forever, but it's not. We're actually almost done. But let's go to the next one. So what if we do 1 plus 2? In order for the product to be smaller and x is less than or equal to y is less than or equal to z, there's only one number z can be. It has to be 2. Plus w is equal to, that would be 4w. And so we get 5 plus w is 4w. We'd get 5 is 3w. And w is 5/3, which is a decimal, so no go. All right, so I think that's it, because what else could we have? 1, that's it, anything else. So there's our solutions. Okay, so what was interesting is that's a nice opportunity to generalize. The proof of the first case really gave us a pathway to finding more solutions. I thought there was another solution here. 1, 1, 1. Maybe I missed it. Let me know. Oh, it says there's only one. So going further, and maybe some of you can find this research project for me. Instead of me searching, I just made a video. The 5 variable case has more than one solution. It has 3. The 6 variable case only has one solution. The 7, 8, 9, all the way to the 23rd case only have one solution. all have more than one solution. The 24 variable case has one solution. So you might think about that a little bit. Let's maybe the 5 variable case. 1 plus 1. I remember realizing that you could always do something like this. So what's that going to be? A lot, maybe a 5 here. Yep, that works. 1 times 1 times 1 times 2. So this is why there always is a solution, because you can always do that. That's the 5 variable case. The 6 variable case, you can do this. Oops, I need one more 1. 1 times 1 times 2 times 6. This is 10. This is 10. This is 12. This is 12. So I'm showing you a way you can always get a solution. Do 1, 1, 1, and then 2, and then 6, or 1, 1, 1, then 2, then 7, and so forth. That always gives you one solution, but what's interesting is there are situations when there's more than one. I didn't prepare this to think about another solution. Maybe you can tell me in the comments below if you can find other solutions for the 5 variable problem. There's 2 other ones. But the open question is this. As it gets bigger and bigger, that little testing we're doing, there's going to be more testing to do. And yeah, you can write a computer to do it, but that's still going to have some limitations. So the only known cases that have unique solutions are 2, 3, 4, and we found those unique solutions, meaning there's only one solution there. And then 24, 114, 174, and 444. And those have been proven just by testing all the cases and finding there was only one. But no other examples of unique cases have been found. So everything else has multiple solutions. And at the time, and I'm sure this has been tested way farther, it had been tested out to 13 billion. So the question is, can you prove that the 444 variable case is the last case ever with a unique solution? And you can start to see the challenge of a proof like that, which is you can't just keep testing because you'll never finish testing. So you'd have to come up with a proof that shows for some reason there will always be multiple solutions. And there's sort of a probability argument. It becomes more and more likely that there's many solutions the more variables you have. But that still doesn't prove it. So any proof that even says you're likely to have lots and lots of solutions doesn't help. So there's a lot of math problems like this where we've seen something, we see that there's some special cases, we think it ends there, but we can't prove it. So I think that's a nice journey through. All they did was a couple inequality things and some testing. And so I remember that project and thought it was a nice exploratory project that you could kind of present to anyone who knows a little bit about inequalities, maybe has wondered about 2 plus 2 is 2 times 2. So I was proud of this project and glad that I found it and got to make it live on a little longer. And if anybody can find me some of this research data or wants to run some experimentation for me, there's a funny little project you can do for one of your classes. All right, hope that was interesting. I'll keep searching my files for projects I did many years ago and just happy to bring them back to life. All right, so there's the first 3 examples where sums and products are equal. And I encourage you to play around with it more. All right. Keep exploring, keep generalizing. Thanks for listening.